Yeah, so people are arriving, so we can just wait a bit. Maybe we wait one more person. So it's taking some time. Maybe we should. Okay, let's then start. So the first speaker of the evening session or afternoon, I don't know, night session is Subodh Patil, and he's going to tell us about spectral distortions as a proof of gravitational waves and physics beyond standard models. So whenever you are ready, please go ahead.
Thank you, Yvonne. Thanks everyone for joining this evening. I apologize for not having been able to join earlier in the workshop. It was a bit of disorganization on my part, actually, and well, we also had a committee visiting us this week at my university, but it's nice to be here and talk about physics. I want to give you an overview talk about spectral distortions, what they are. You may have never heard of them, and how they can actually provide us with a very interesting, in my opinion, probe of physics beyond the standard model, not available, at least to my knowledge, through any other means, and also of gravitational waves at frequencies which are also not probed by any other means. So I'd like to sort of begin with just a review of the cosmic microwave background. I think you're all familiar with it. Well, certainly it's anisotropies, and it is the cleanest probe we have of fluctuations in the early universe. Clean in the sense that we are looking at extremely linear modes. There are some foregrounds that get in the way. We have to be mindful of those foregrounds, but once you're able to peer directly at the microwave sky, you notice two things. Firstly, that it is, and in fact, this is the first thing that we may have heard about in our cosmology courses when we're undergraduates, or maybe even in high school, that there is a relic radiation from the Big Bang, and it is of a black body nature. A very perfect, close to perfect black body nature, in fact, with a temperature of about 2.7 Kelvin, which is bounded to be perfectly black body over all the frequencies we've probed to 1 part in 100,000. Coincidentally, it also, that's the same level at which we've noticed that there are angular anisotropies. So if you look at different angles in the sky, you'll notice that there are patches that are slightly hotter and colder, which again fluctuate to 1 part in 10 to the 5. So by hotter and colder, I mean you look at a different patch of the sky and you would see another black body spectrum with a slightly temperature. And of course, those anisotropies are a photograph of acoustic vibrations in the early universe when at the moment of last scattering, or the epoch of last scattering, it lasted about a window of about 50 Z of about 50. But effectively, it's a surface. It's a flash, and it is not an analogy. It is literally an ultrasound of the universe when it was a baby. So if we step back and ask what is the information content of what we're staring at? So there are, if you look in every different direction, you see these fluctuations. They are limited in resolution because what happens when you get to less than about 1,000, 1/2000th of a solid angle in the sky is that you start to resolve structures, stuff, astrophysical things that are shining back at you or scattering CMB photons. And so that sort of limits the resolution. And these things correspond to, of course, the clusters. And so because we're limited in resolution, and of course, we're limited in the biggest scale we can see, which is our cosmic horizon, we have about 10 to the 6 pixels in the sky. So if you have an incident beam of radiation, you have essentially 10 to the 6 pixels where you can sort of get this incident radiation. And there are 3 bits of information characterizing this radiation, which is its polarization. There's E, and then there's B polarization. It's just 2 sort of decompositions in a particular basis. There's actually another one, circular polarization, but there is no known astrophysical process or cosmological process. No one that you don't go and cook up that could generate it. So you just think that you're done. That would be it for the information content of the sky. Literally 10 to the 6 times 2 pixels of that order. But that's assuming that there's one number that characterizes its spectrum, that is the temperature. And that is certainly true if the incident photons are purely of black body nature. So clearly, if there is any deviations from black body, this is opening up an entirely new dimension or dimensions of information that we have, in fact, yet to really access. So insofar as the CMB is a finite thing, there is only one sky. There's only so much resolution we can probe in terms of anisotropies before we're really looking at astrophysics and nothing primordial. The last remaining stand of the CMB is its spectrum. So I think, yes, I guess I anticipated this slide a little bit. So why are we limited in resolution is essentially 4 grounds. And what is interesting from the perspective of somebody who's interested in, let's say, BSM physics, is that if you look at very, very small angular scales, the CMB sort of damps out. I'll explain that in a second. But the nature of that damping is very sensitive, in fact, to neutrino masses. It's not very sensitive, but our observations are getting sensitive enough to start to compete. And the way massive neutrinos actually affect that damping tail is that it actually affects essentially the number of, it affects N effective, the number of relativistic species. The more massive the neutrinos are, that number sort of deviates from 3 point whatever. And of course, its phase shifts a little bit. So by accurately measuring that damping tail, and if we determine it entirely, we may actually be able to measure a BSM parameter if neutrino masses are generated by the so-called Weinberg operator. Indeed, the spectrum of the CMB is almost really unexplored at this point, except for the fact that we know that it's a black body. And it, in fact, is expected to deviate. So this is something that you may not know, or if you do know, I'm going to review it in a second. We are actually expecting to see deviations to the part in 1 billion to about 10 million. And that follows just from, if we just assume the vanilla lambda CDM model itself. So so how can this happen? Well, recall that a pure black body spectrum is determined only by one number, that is its temperature. So you change the temperature and you change the spectrum. It's completely determined by that one number. Distortions, of course, are characterized by if you, at any given frequency, if you have some deviation from the functional form of a pure black body. very seminal and deservedly famous observation by the COBE-FIRAS collaboration found that the spectrum is in fact consistent with a black body to the 10 to the 5 level. But a moment's reflection suggests that any injection or extraction of energy in and out of the photon bath that does not thermalize efficiently enough before recombination or after last scattering will produce distortions. So here's a laundry list of different things that could have done that, and in fact does do that. So reionization from the first stars ends up rescattering CMB photons. That's, if you like, somehow quote unquote known physics or astrophysics. But there could be all sorts of things that you haven't entertained yet or thought of, such as very late time decaying particles. Late time meaning that they decayed within the window in which any injected energy into the photon bath didn't have time to thermalize. You could be very sensitive to axion photon conversion. There are possibilities that the primordial spectrum that gave us sort of the primordial fluctuations that seeded the scaffolding really for dark matter on which all the galaxies that we observe in the night sky form. If that somehow wasn't exactly scale invariant, or even if it was scale invariant, there is some distortion generated from that, and so on. Okay, so I could keep going. I just listed a few that are sort of spring first to mind. But the most important thing to note is that within the standard thermal history of lambda CDM, there is predicted to be a distortion signal. So reionization from first stars. So what this plot is if you like, these are units that radio astronomers love to use, and I can't stand. It's delta I. It's really the change in the spectrum. But in these units, Jansky's per steradian, I have really no idea what they are. But if you just sort of look at this plot, let me just guide your eye here. This is about a 10 to the 6 distortion. This is about a 10 to the 9 distortion. I think they go roughly linear. So reionization itself predicts, depending on the frequency. So the CMB itself peaks at 160 something gigahertz. And this is what the change in the spectrum would be just from the reionization signal. There is also the possibility that the actual primordial spectrum, what it corresponds to are acoustic modes in the primordial plasma, and these dissipate. Okay, so just like if you stand in the middle of a room and you say something, eventually that sound dissipates, right? It goes away. And what does it dissipate into? It dissipates into heat in the ambient air. So you've injected heat into the air around you. And in the same way, acoustic vibrations in the early universe, the longitudinal excitation that we see in the anisotropies, that also dissipates and that heats up the plasma. And so there is a signal from that expected as well. And then there's these the wiggles. Actually, maybe that's my next slide. These little wiggles correspond to lines that appear from the different transitions as hydrogen starts to form. So because that process, because hydrogen has a very, very well-known spectrum, there are these wiggly sort of distortions that you expect at the 10 to the minus 9 level. So this is just within the standard cosmological scenario. So this is a slide actually I borrowed from a talk by Dale Fixon at a workshop we both attended a few weeks ago. This is FIRAS's results now plotted as a function of frequency. They bounded a distortion signal. Okay, so this is about the 10 to 6 level at these different frequencies, and this is hilarious, right? So they almost just skirted above the signal expected from the so-called Y distortion. So it's remarkable that FIRAS constrained the FIRAS, of course, standing for the far infrared absolute spectrometer. It's the accompanying instrument that went up with COBE. They constrained that the universe was almost a black body, but they could have almost seen a signal. So you can understand the frustration of people who are interested in going out and looking for these things, which is we almost seem to be there. Can we do better? And if I have time at the end of the talk, you can ask me about what experimental efforts, what observational proposals are on the table right now. So there's another. So if you're not really interested in cosmology or astrophysics and you're sort of a BSM person and you're interested only in particle physics, let me advertise to you that there is a very unique and interesting window that spectral distortions offer you, which is that any particles that decay in this window in terms of redshift. So this roughly corresponds to time lifetime for particles, about 10 to the 6 to 10 to the 14 seconds. If they decay in sufficient numbers in that window, you are generating, and they have any sort of branching ratio into the electromagnetic sector, you will generate spectral distortion. So of particular interest are gravitationally suppressed decays. These are ubiquitous in any theory where you have extra dimensions, or string theory, where literally if the only numbers you have available to you are m-Planck squared, and the mass of your purported particle, there's only one combination that you can use to form a timescale out of it, and it's given by m-Planck squared divided by m cubed. And if you stick in some numbers, you will find that particles that have gravitationally suppressed decays of them between the masses of 100 GeV to 100 MeV decay precisely in this window. So gravitinos have, of course, been studied as a potential source of spectral distortion, but there's many others. If you have a particular string cosmology where you have moduli fields, dilatons, KK resonances that are decaying in this window, there is a shot for you to constrain your scenario. And I advertise that there are actually a plethora of papers to write, revisiting quite a few old models. And this is showing you the sort of sensitivity you could get for a PIXI-like survey, right? So this roughly corresponds to the mass window anywhere between 100 MeV and 100 MeV and 100 GeV. And this is telling you really just like, if you have even a very, very tiny abundance relative to, it does not have to dominate the universe in any sense, but it has to be around some level, and it has to have some level of a branching ratio, you can have constraining power. So we've constrained extra dimensions fairly well at colliders, but we're very bad at constraining warped extra dimensions. They tend to be flat. I mean, and if they're warped, of course, it's very model dependent. So this is a potentially complementary window. So in the remainder of the talk, I just want to sort of review briefly the basic physics of distortions, what the different types of distortions are, and how, in fact, they provide a stochastic, a means to detect stochastic gravitational waves in the sky in a frequency range that you really cannot touch with anything else. Of course, it's not particularly sensitive, but it's probably the only thing we'll ever have at those scales, at those frequencies. And if I have time, I may just touch upon a laundry list of various phenomenological scenarios that I imagine various people online right now may have thought about: axions, cosmic strings, phase transition, and so on, in various dark sectors that you could also constrain. So, so I'm just going to have so this is sort of getting into just a quick primer of spectral distortion physics. So a black body spectrum we're all familiar with is given by this functional form. And if you imagine if you're in a, if you have a perfectly black body spectrum, I just start throwing in photons. If I just start adding photons at different frequencies, if I add photons with precisely the number density at any given frequency such that I'm basically matching this functional form, I can just shift this temperature. So if that's true, then you're just simply, if you're injecting photons that already have precisely this thermal character, I'm just simply changing the temperature redshift relation. But if it's not true, then some sort of distortion will result. I'm going to have some sort of a spike or a dip in the spectrum. And there are two main types of distortions that we consider. One is the so-called mu distortion, which effectively looks like a chemical potential. Like you've just shifted the Bose-Einstein distribution to have a non-zero chemical potential. And it becomes important at redshifts of above 50,000, okay? And by the way, I have to stress, when I saw that spectral distortions are a probe of physics between redshift of about 1 million to 50,000, that's when me personally, I got hooked. Okay, I thought, wow, this is amazing. There's no other way that we'll ever be able to probe the universe at those scales. and that was the sort of the hook that got me into this field. There's another type of distortion, a generic type of distortion called so-called Y distortion. And it's important, again, at redshifts less than 50,000, where scattering is inefficient. And I'll explain the physics of it in a little more detail in a second. But the easiest way to think about it is if you imagine two black bodies, spectra, from different parts of the sky, coming at you as an observer with slightly different temperatures, and you look at the combined spectrum, the combination of spectrum will not be black body. It'll in fact have a sort of a deviation on the wean tail, and that is what we know as a mu distortion. How do these different types of distortions arise? So in the early universe, Brahms-Strahlung and double Compton scattering can basically change the photon number in the early universe. Whereas Compton scattering does not change the number of the number of photons, but what it does do is it redistributes them around phase space. So what happens is at redshift of about 1 million, Compton scattering is very, very efficient. You basically thermalize anything extremely rapidly. Whatever you try to throw in, whatever you do, whatever modified thermal history you have, you thermalize, and you wouldn't know any better. You just modify the temperature redshift relation. And that's all you see at the end anyway. So you're effectively, blind to that physics before. But after redshift of about 10 to the 6, when Compton scattering is no longer so efficient, you can generate a distortion. So there's a very nice so-called thermal Green's function formalism pioneered by Jens Kluba. You can calculate, given a particular energy injection history into electrons, really, that as a function of redshift, you can go ahead and calculate how much distortion you're going to get as a function of time. And you find that you not only can generate these two sort of canonical forms, so-called Y and mu distortions, what looks like a chemical potential or a modification to the wean tail, but all sorts of intermediate shapes that give you back via this Green's function approach an indication of the energy release history. So the thing that I think if you're an early universe cosmologist, you should pay the most attention to is how spectral distortions are a very powerful probe of very small scale physics beyond that which CMB anisotropies probe. So CMB anisotropies tend to cut out at around co-moving scales of about 0.1 inverse megaparsec. Before that, foregrounds just become dominant. Why do they become dominant? Well, it's about to be explained here. But spectral distortions actually allow you to be sensitive up to about 10 to the 4. So if you think inflation was the model of the early universe, this adds about six more E-folds of the factory that's producing those modes visible to you. You get to see these modes being produced, or some limited information about them for 6 more E-folds. So that's really cool. So here is a very simple way of understanding how you generate spectral distortions from small scale power. So this is a plot pulled out from a very old paper. It's a very nice paper, actually, by Wayne Hu and Martin White. This is the famous acoustic peaks that you get for CMB anisotropies if you had a scaling band spectrum. And the reason they decay is what is known as silk damping. So the last scattering surface has a finite duration, so that every photon undergoes sort of like a random walk before it sort of free streams towards you. So you're smearing out very small scale resolution. But if silk damping did not happen, you would have seen this. Okay, so where does this power go? This power goes into heating. So these acoustic vibrations, have gone into dissipating energy, and that's what generates. Yes.
So what have to say that you have about 3 minutes or 4?
Yeah, no problem. No problem. Okay. So this dissipates energy, and it results in distortions. I think what I would and by the way, the same thing happens for tensor perturbations, but tensor perturbations dissipate only through free streaming and not free streaming and scattering. So acoustic vibrations also change the energy, the local density. And so Thomson scattering, the rate of Thomson scattering changes as a function of position, whereas tensors do that far less efficiently. And this is what spectral distortions can buy you. They give you constraining power. If you imagine a probe class mission of small scale power at scales that you would never have seen before. They do the same thing for gravitational waves, because any gravitational wave background also generates a distortion. And this is what a probe class mission would have constrained for you over frequency scales that we literally just don't have any astrophysical detector in the sky at all. At the largest scales, there's going to be anisotropies. And if it wasn't for such spectral distortions, we would forever have been blind to this window. So I wanted to discuss at some point, well, I mean, I've run out of time, but let me just sort of, you can ask me later if you like, that alone allows you to put constraining power on all sorts of interesting early universe scenarios involving axions, first order phase transitions in the dark sector, cosmic string network collapse. I don't have time to get into it, but let me just conclude with where we are now with what is the status of observations. Is we have been given a very strong encouragement and green light from a very high level ESA panel that has given a recommendation that funding a probe class mission for spectral distortions in the next large call, Voyage 2050 means it could be up till 2050 before it flies, so it's quite a medium to long term goal. That's something that is a very real possibility, and we are very much at this point getting organized for how to actually go about this. So I think I will conclude here and just tell you, so I guess I did not get into too many details as much as I would have liked, but if there's anything you remember from this talk is that spectral distortions, if you've never heard of them, offer a new portal for gravitational wave cosmology. It's not the most sensitive detector in the world, but it is the only detector we will ever have at frequencies interpolating between B modes of CMB anisotropies and pulsar timing arrays. And this gives us a very interesting constraining window on DSM scenarios. So thank you very much for your attention. I'm happy to take any questions.
So thanks very much for the very interesting talk. That's really interesting. So is there any question from the audience? You can also, I mean, either speak or write in the chat box. So feel free to ask any questions. So there is time for questions if there's anyone. So let me maybe start while people collect their ideas. So in principle, so do you have like I mean, you have this laundry list, but you have like what kind of distortions each thing? I mean, you mentioned there are these two classic Y and mu type, but there may be many in between. Do you know at this point what kind of other shapes, or could you, yeah, I don't know, how would you know?
Yeah, so they're these so-called R-type distortions. They're so-called residual distortions that interpolate between the two of them. So asking how something deviates from a black body is the same as asking as how can something be non-Gaussian. There's an infinite number of ways, right? Yeah. But if you have a particular, so if you think of any particular physical process, typically it's something decaying or something dissipating. The functional form, you can put a fairly strong prior on the types of distortions you would get. The mu and the Y are a generic sort of universality class that lots of things end up producing, something that looks like that. You will, of course, produce other types, but I think at this point, just detecting even one of them would be very, very cool, I think. I think these recombination lines that I kind of just flashed here, these sort of little wiggles, what's really cool about them is that they have a wiggle. So you can actually maybe even entertain doing this from the ground, because so this is actually a very different type of distortion, right? This is just a wiggle. This comes from literally just seeing hydrogen lines pop in. So this would neither be Y nor mu. It's the recombination line. And people are entertaining because they're wiggly. You can do relative, you can do differential measurements and not absolute measurements, and that's easier. And there's a nice window where the atmosphere is relatively quiet between, I think, 2 and 6 gigahertz that a group in India and Bangalore is actually trying to do via interferometers. So, yeah. So to answer your question, look at all these different ways. Yeah, there's many ways.
Yeah. Great, that's very interesting. So, Basa Bendu.
Yeah, hi, can you hear me?
Yep.
Yeah, hi. So thanks for the very nice talk. So I have one question. So in the laundry list, you mentioned some of the particle physics motivation for this kind of searches. And there you told about something like a decaying particle species, which can be like decaying through some gravitational portal or something like that. So my question is that do you want this the decay final states to be specifically photons, or can it decay to any
yeah, so what happens is, you see, so what you have is a photon baryon plasma that's undergoing whatever it's doing, and some tightly coupled approximations, like the electrons are basically tracking the baryons, and anything with any, so you do need some branching ratio to our electromagnetic sector, that's for sure. But precisely whether you go straight into photons or go straight into electrons, it doesn't matter, because they tend to interact with each other and very quickly produce a very generic type of distortion signal that either looks like Y or mu. So you do need a branching ratio to electromagnets.
Okay, so just to be a bit more specific, suppose like if I have some decaying particle which is decaying 2 photons, but with a very tiny branching ratio to dark matter as well. So in that case, it can also constrain some dark matter final states,
Yeah.
right?
So here is the plot that will, I hope, try to quantify that. So this is this is a Pixie-like survey, right? Roughly think of this as a decaying particle of mass 100 GeV, and over here is about 100 MeV. And this visibility is the mass times the branching ratio into photons, and this Y is the entropy ratio, the Welig density of species, whatever this decaying species is relative to the entropy density. So over here, this combination has to be anywhere down to 10 to the minus 16 level. How you shuffle them between having a large or small branching ratio to this amount of stuff, that's the amount, that's the window you're trying to, that's the needle's eye you're trying to thread. So for instance, you have a gravitationally suppressed decay, you could just decay into let me think, could you decay straight into gravitons and then gravitons? I have to think about that.
I got your point, thanks.
Yeah, at the end, if these numbers are above this line, you're in business.
Okay, yeah, thanks.
Okay, so Anish, maybe your question is a quick question. Oh, we can't hear. I don't know if you are speaking. Maybe I can read it. So he was just asking, I hope this is the same. Any prospects for detecting non-Gaussianities from spectral distortions?
In fact, indirectly, yes. So this is something that others have thought about much more than me. I have only been discussing the monopole signal, right? So I've only been discussing, what if you take a sky average of the sky and look for distortion. This is most of what you saw in my talk. What you can also do is look for cross correlations between, let's say, a mu distortion at a given angle in the sky and other CMB anisotropies. And those cross correlations, once you deconvolve them, are sensitive to higher endpoint functions, not just scalar non-Gaussianities, but also tensor non-Gaussianities. But of course, you need all of these things to conspire to give you something within the window of detectability. But yes, the short answer to your question is yes. Is it generic? No, I think you have to go. So if you have like the generic scale invariant, very weak non-Gaussianity, you're not going to see very much. But if you have very scale dependent non-Gaussianity that picks up at scales that are far beyond CMB anisotropies, you may get some cross correlations, let's say mu T or mu E cross correlations that may be sensitive to them. So a way to think about this is mu is effectively a convolution of a 2-point function of either scalars or so on and so forth. And so if you have mu times a polarization, you are sensitive to non-Gaussian. So cross correlations could.
So from CMB, we know that the non-Gaussianity should be small enough, like of the order of 10 or less than 10, 5. I think the number is at least FNL.
So this precise statement is the FNL estimator is bounded to be below that at CMB scales. Yes. Yes. I would not go from that to say that there is no non-Gaussianity already at the CMB scale.
Yeah, of course. So then is there a corresponding number also one can take from these measurements of Ferras and the other things that you are showing? That is there a corresponding number also?
Well, okay, so I think some groups have actually tried to look at, okay, maybe not Ferras, but I think people have tried to look at cross correlations. So Planck actually, believe it or not, can give you some very, very not completely bad constraints on spectral distortions simply because it has multiple frequency cover, right? It needs to go over multiple frequencies to cover, to get a handle on dust foregrounds. So there are some constraints already available there, and they're actually more interesting than you think. But they're still obviously nowhere near sensitive enough to the level of detecting FNL to, order 1. I think that's completely science fiction. Yeah. But a probe class mission, I think, could get there. But I think probably if non-Gaussianity is your focus, there are probably other things you may want to focus on, including large scale structure.
Yeah, sure. But in the large scale structure, I would believe the astrophysics plays a yeah.
Let's continue maybe in the discussion, since we will continue after the last talk. So Lauren, could you share your slides?
Absolutely.
Yeah. And sorry, we should thank also Subodh again. So we'll continue. After this talk, we will continue with questions. Okay, so then
see my slides.
Yeah, we can see them, and I think we can hear you well, so it's perfect. So, okay, our last speaker of today is Lauren Pearce. No, I don't know how to, sorry. And she's going to tell us about inflation-related gravitational wave signals in the afflecting baryogenesis. So please go ahead.
Okay, I'd like to thank the organizers for the chance to be here and give a talk. My talk is a little bit less related to inflation and inflation, gravitational waves, and black holes than the earlier speakers. We'll talk a lot about gravitational waves, but basically the main takeaway here is that one of the signals that we saw right before the break having to do with gravitational waves can actually occur in much broader scenarios, and I'm going to talk about one of them today. So since this is the inflation section, I figured I would start just by saying that inflation is here kind of in the background. It's providing a lot of the tools that show up here. So first of all, inflation provides the background of gravitational perturbations and, more importantly, scalar perturbations, because I'm going to be using the same mechanism as our earlier talk, known as the poltergeist mechanism, that get enhanced later, as we'll talk about. So inflation is key in providing that spectrum that gets enhanced. More importantly to the scenario I'm looking at, it also provides this epoch right after inflation of scalar field evolution. So we have people from a lot of different areas here. So just to kind of remind us how this works, during inflation, if you have a scalar field and its potential is relatively flat, it's going to random walk out to a pretty large VEV during inflation. The large Hubble prevents it from relaxing down. But at the end of inflation, the Hubble parameter decreases as we move into radiation domination. And so the scalar field that had the large VEV is going to relax down to its equilibrium value. And so interesting things can happen during this epoch. I'll be talking about one of them. But of course, a question that we have with all of this should be, what sort of observational evidence can we find for any of this? And I'll be looking at particularly gravitational waves as one potential probe. So in this epoch of post-inflationary epoch of scalar field evolution, one thing that it can actually do that has attracted a lot of attention over the last 40 years or so is generate the observed baryon asymmetry of the universe. This is known as afflectine baryogenesis. It predates me. So here, basically, it's the same kind of picture that I outlined above, where we're going to specifically use a complex scalar field that gets the large VEV and then relaxes afterwards. And in terms of putting this into a bigger particle physics picture, you don't need to, but if you already like SUSY, these sorts of potentials with a flat direction show up very generically in SUSY, whether or not you have low scale SUSY or high scale SUSY. So you can have this with high scale supersymmetry. And if you're doing this in SUSY, then the scalar field that gets the large vacuum expectation value is made out of squarks and sleptons. And that means that its VEV is going to spontaneously break C and CP symmetry. And so then when it relaxes, we have all three of the Sakharov conditions satisfied, C, CP broken, along with time evolution. And so that means that when the SVEV relaxes down and the condensate fragments, it produces a baryon and or a lepton asymmetry, which is nice because the universe has an excess of baryons. Now, this fragmentation process can directly produce gravitational waves, and it's been argued that these are potentially observable. That's not actually what I'm interested in this talk. The gravitational waves that I'm going to be talking about come from a different source that I think might be a little bit more accessible. And that's because of what we're left with after this Affleck-Dine baryogenesis, okay? So naively, we were left with baryon number, but we can ask, what is that baryon number actually in? So that scalar field, it carries some sort of global charge, namely baryon or lepton number. And when we have this sort of scenario where we have a scalar field with a relatively flat potential, then generically QLs exist in that scenario. So specifically, the condition is you look at the potential over the field squared, and if that is minimized at some non-zero value, then the lowest energy state is not actually a bunch of free scalar quanta, but this non-topological soliton known as a QL, okay? And conceptually, what you're checking when you evaluate this is just that a scalar quanta can lower its energy by being inside the QL, okay? Then its mass energy would be outside the QL, okay? And this happens very generically for the sorts of scenarios that we're interested in where we have Affleck-Dine baryogenesis, because that potential tends to level out. And this is true whether you want to break SUSY via gravity mediation or gauge mediation, although the types of non-topological solitons you get, they can look rather different. So because of this, in Affleck-Dine baryogenesis, when that fragmentation of the condensate happens, it doesn't fragment down into individual scalar quanta carrying baryon or lepton number. It fragments into QLs, these non-topological solitons that then sit and wait for a while. When I present my results on the QLs, there's two parameters that basically we care about. The first is that thing that we minimized times the square root of 2. That's just the energy per unit charge of the QL. And then of course the VEV inside the QL that remains non-zero, the two things that we care about. So having hopefully shown or convinced you that the final state of Affleck baryogenesis, at least for a while, are these QLs, how is that going to be connected to the topic here, which is gravitational waves? So what's making our gravitational wave signal? Well, so these QLs, they're big and heavy, and so they generally lead to an early matter-dominated epoch. And then, as I'll argue, this epoch actually ends rather rapidly, okay? And as we learned in the session before the break, this can lead to resonance-like peak in the gravitational wave spectrum, okay? And some of the papers, this is known as the poltergeist mechanism. You may have heard it under that term. And so this is the gravitational wave signal that we're going to be interested in here. It's been explored in the context of primordial black holes, but as I'll show, these QLs can make the same sort of signal and perhaps have a better motivation in terms of Affleck-Dine baryogenesis. Okay. So to understand this better, we have to kind of look at what the population of the QLs look like, because when the condensate fragments, you can get QLs or anti-QLs, whether they carry baryon or anti-baryon number. And that depends on whether the VEV as a whole goes clockwise or counterclockwise. Now, one of the things that we know from simulations and from the fact that QLs are the lowest energy state is that the vast majority of the condensate's energy goes into these QLs. But if we want a very small charge asymmetry, then we're going to have a large symmetric component when we look at these QLs. So in the results that I show, I'm going to have both the charge asymmetry, but also kind of the population asymmetry of the QLs, which is given by R. And generically, that should be about the same order of magnitude as the charge asymmetry. What this is connected to in terms of like, if you like to picture what's going on with the VEV, is the VEV is following a highly elliptical orbit, and that's what gives you this very small charge asymmetry, Okay. Another way that I like to think about this is that the overall VEV is going to follow a highly elliptical orbit, but that's averaged over many, many patches. And each individual patch, the VEV will be going clockwise or counterclockwise, and that will lead to QLs and anti-QLs so that you end up with this population of both that has a small asymmetry between them. Okay. And we'll see why that large symmetric component is important when we actually get to our numerical results. Now, of course, these QLs can't be absolutely stable because we need to get that baryon number into the standard model particles that make up galaxies and stars and you and me. So the QLs are not going to live forever. They're going to eventually decay. They tend to be long-lived. And the reason why this works, that we can have these QLs, but they ultimately decay, is the QLs are not allowed to decay into scalar quanta. That's the condition for them to exist. However, the scalar quanta inside the QL can still decay into a fermion plus a neutralino or chargino. Okay, so the energy per unit charge omega is less than a free scalar quanta, but not a free fermion plus neutralino or chargino. And so that means that these QLs can kind of evaporate as the individual charge in them decays to a fermion that then leaves the QL. If we're talking about SUSY QLs, then we're talking about going to a quark or a lepton and then neutralino and chargino. And we parameterize this with an effective coupling because it's going to depend on what lepton species or quark species are involved and how you break SUSY, all of that mess. So just have that parameterized with an effective coupling. Now, even though they decay, in order to dominate the matter density of the universe, they have to live for a while. And so we can say, well, why are these QLs long-lived? One reason is just that, that effective coupling, it tends to come from the standard model Yukawas. It might very well be small. But there's more beyond that. And that's that if we look at the simulations, the initial QLs that we start with are very, very large. If we're looking at a gauge-mediated scenario, then when that condensate fragments at the end of inflation, all the charge in one Hubble volume ends up in a single really, really huge QL. We're talking about like 10 to the 30 or so charge in the QL. For gravity-mediated scenarios, the simulations are a little bit less conclusive, but still generally about 1,000 QLs. So we're ending up with very, very large QLs that will take a while to evaporate. And why it takes a while to evaporate is that this decay actually generically only happens on the surface of those huge QLs. So there's a surface to volume factor there. And that's for one of two reasons. The first one is inside the QL, we still have a non-zero and often very large VEV. And so those fermions are heavy inside the QL, which can kinematically forbid that decay that we're interested in. So that only happens at the surface where the VEV is dropping down to 0. The second reason is that even if the decay is allowed in the surface, you're producing a fermion that's around all these other, 10 to the 30 or so scalar quanta that interacts with. And so it can take a long time to diffuse out, filling up the Fermi sea and turning off future decays inside the QL, leaving us again with decays only at the surface where that fermion is able to stream out efficiently. So when we look at these QLs, they're going to live a long time because the decay happens at the surface. And this actually leads to behavior very similar to primordial black holes. So for a thin wall QL, the radius goes as the charge to the 1/3 power. And so that means that our charge depletion rate goes as the area, so it goes as the radius squared, so the charge to the 2/3 power. And when we ask, when does that QL efficiently decay? Okay, so when should we think of these things as decaying in a cosmological context? The charge per unit, the decay rate per unit charge has to be bigger than the Hubble parameter. And so if we look at the left-hand side, it actually scales negative as a negative power of the charge. So effectively, if we're thinking about the decay of the QL per unit charge, it speeds up as the QL evaporates. And so that means that it's rather like black holes whose decay or evaporation speeds up as they become smaller. The terminology thrown around for this is it's effectively instantaneous. Once it gets to that point, those QLs are gone. Okay. So what this means is we have QLs that start off very, very big, very, very heavy, and they're long-lived. So we generically have an early matter-dominated epoch. Here's the temperature that it would start at just by setting up the energy equations. We can use the condition for them not to decay before this temperature. And that gives this condition for the gravity mediated case where we're kind of assuming, well, so this factor here, it will be 1 in the gravity mediated case. Okay. As long as we have that large symmetric component, which we generically expect, then this is very easy to satisfy. If you don't have that large symmetric component, then that 7/3 power of the asymmetry in the denominator can really hurt you. But we find that as long as we keep in mind that we expect the energy to give us a huge symmetric component of about the same size, then we satisfy this condition very easily. And so we do have our early matter-dominated epoch relatively generically in Affleck-Dine scenarios. If we want to talk about how it ends, it's not just enough to show that the individual QLs decay rapidly, instantaneously. We need to know that the population isn't spread out, because if the population of QLs is too spread out, then the early matter-dominated period will slowly end. Okay. And here, the initial QL mass spectrum from simulations, it suggests that it's very sharply peaked. This is especially true in gauge-mediated scenarios where all the charge in a Hubble volume, when that condensate fragments, goes into a single QL. In gravity-mediated, it's less clear. The simulations that have been done, I'm not aware of any that really look at a highly elliptical orbit, but the simulations that have been done still seem to show that the spectrum is pretty highly peaked. So putting that together, that means that we have this early matter-dominated epoch, and it's going to end very rapidly when the QLs instantaneously decay. In the results that I show below, we do take into account the fact that this decay is going to dilute the baryon asymmetry. So why is it important that we have an early matter-dominated epoch that ends rapidly? And we heard about this before in the talk before the break, so I'm going to go through this relatively quickly. Just as a reminder, or for folks who came in late, who missed that, the primordial scalar fluctuations from inflation can source gravitational waves. And if we have a matter-dominated epoch, the modes that enter the horizon during that epoch can grow, and the ones that enter the earliest are the most enhanced. So those grow at the end of that early matter-dominated epoch. They have sourced gravitational waves. And so we can ask what the gravitational wave spectrum from those scalar perturbations look like. And, you know, I'm referring to 2 papers by our earlier speaker. So, you know, I'm glad he gave a talk on this. If it has a gradual end, then it turns out that spectrum is suppressed. There's an extra suppression there. But if there's a rapid end, like I just argued we have in this Affleck-Dine case, then we have this extra resonant-like peak, which is very, very interesting and very, very promising for detection. Conceptually, the way that I like to think about this is that we have matter density perturbations that grow during the matter-dominated epoch. And then when the QLs decay, I mean, the matter density perturbations are the QLs. So these overdensities suddenly become relativistically moving sound waves. These sound waves have their enhanced amplitudes when they oscillate during the radiation-dominated epoch that follows the matter-dominated epoch. And so they can act as a source to resonantly enhance those gravitational waves that are co-moving with it. That's the way I think of it conceptually. Okay, so I want to make sure to have time to talk about the results, so I'll just briefly mention what the parameters that we play around with are. We have the QL parameters that I introduced earlier. We have the baryon asymmetry and the QL asymmetry, okay? Like I said, we expect this to be the same order of magnitude, and we want to make sure we get the final baryon asymmetry that matches observations. We have a little bit of room to play around with the number of QLs per Hubble volume at fragmentation between 1 and like 1,000. And then the main thing that we can play with besides the QL parameters is the reheat temperature. That ultimately determines the initial radiation energy density, and so that's going to determine our equality temperature. And then, of course, the effective Yukawa, and that's going to, in turn, determine the decay temperature, T decay. Here are some of the calculated parameters. So here we are in the process of doing a full parameter space search, but we did publish with some benchmark scenarios here. So you can see the same sort of shape that's hopefully familiar from the gravitational wave spectrum. With that resonant-like peak, which turns out to be, for our benchmark scenarios, well in the LISA and DECIGO space. What does the signal depend on? It depends strongly on the equality temperature. That sets the frequency range of where this peak is, where the early matter-dominated epoch starts. And it especially depends on the length of the early matter-dominated epoch. So the ratio, the height of the peak goes as the ratio of T decay to T equality by, I believe, like the 7th or 8th power. And so it really sets the amplitude here. As was talked about in the earlier talk, one thing that we do have to be careful about is whether we enter the nonlinear regime, where we don't really trust the linear evolution. So in all of these benchmarks, we chose our points so that the co-moving momentum that enters at the beginning of the early matter-dominated epoch is 470 times the co-moving momentum that is entering at the end. And that's basically the condition to say we're out of the nonlinear regime, so we can trust our results. This is a connection between the equality and the decay temperature. And so basically this observable range, if you take LISA and DECIGO, covers quite a broad range of temperatures here, because it's covering quite a broad frequency range. One thing that I do like to point out is these lower temperatures in the LISA band. If you're trying to do SUSY model building, you might like that because those are preferred due to the Gravitino problem. I do have the 3 lines here. Those correspond to 3 different effective Yukawa couplings, which basically influences where when the early matter-dominated epoch ends. One for a Yukawa coupling like the standard model bottom, one like the top, and one like the electron. Smaller couplings, they decay later, and so that's why they end up at lower frequencies. Okay. Details of what we assumed making this plot. If you care about the parameters, those are there. The specific equality and decay temperatures. So for those plots, we just put in QL parameters. So the last thing that we kind of had to do is go back and check that those QL parameters, omega and the VEV, actually fall nicely out of the sort of potentials that we have in SUSY. So here's just a sample potential from gravity mediated. And it has the 2 parameters, M and lambda. And so we can check those and make sure and find sets of those that match the QL parameters that we use to make our benchmarks. And all of those were done with thin wall QLs because they're nice to work with. And so we did confirm that the QLs that arise in this gravity mediated case are in the thin wall regime where, okay. In terms of future work, something else that we're working on, the reason that we did that with gravity mediated is that gauge mediated scenarios do not produce thin wall QLs. They produce thick wall QLs, and we expect the same sort of behavior with those because the decay rate over charge scales with a different negative power. And so the same story goes through, but we actually have to do a little bit more work to figure out what sort of spectrum we're going to get. And so that is in progress now. Okay, so in terms of conclusions, since this is the inflationary section, remember inflation is behind all this, the prerequisite to get the scalar perturbations that are amplified and make the gravitational wave spectrum for the poltergeist mechanism it's also a prerequisite for Affleck-Dine baryogenesis in terms of driving that scalar field Vev out to large values from which it relaxes from. Affleck-Dine baryogenesis, it relatively generically produces a gravitational wave signal via this poltergeist mechanism. You're going to generically get these Q walls, they're going to generically be long-lived, and then they're going to decay rapidly. So this is relatively generic for Affleck-Dine baryogenesis. And the poltergeist mechanism means that we have this strong gravitational wave signal, at least for our benchmark points that showed up in the observable range with LISA. We're interested, like I said, in doing a larger scale survey of the parameter space. We're also interested in trying to think a little bit about the nonlinear regime, because it looks like a lot of that parameter space is going to be nonlinear. So at least coming up with approximations there. And like I said, we're also working out the thick wall Q walls. So I'm happy to take questions. I know we have also an upcoming panel discussion. So yeah, thank you.
Yeah, thank you, Lauren. Thanks for the talk, very interesting. So yeah, so we have some time for questions for Lauren directly. And after that, we will smoothly connect to the discussion session. So if you have collected questions for all the speakers, I think hopefully all the speakers will be here. But so for the moment, let's in the meantime, just anyone who has questions for Lauren, you can write in the chat box or unmute yourselves. Okay. So while people are collecting their, so there is one question. Okay, let me give you. Please go ahead.
Yeah, can I ask a question? Yeah, thank you for a nice talk, Lauren. And thank you for using the poltergeist mechanism. I have one question. So when we wrote the paper about the PBH evaporation, the PBH evaporation is not, strictly speaking, PBH evaporation is not instant reheating. So we took care of that finite reheating time period. So I'm wondering which is more rapid, which leads the more rapid reheating, PBH evaporation or evaporation of Q-ball?
So that's very interesting, because that's something that we also want to work out. So here, the rate goes as the charge to the -1/3 for the thick wall, or sorry, for the thin wall. I think it's -4/3 for the thick wall. I think, if I remember right, the primordial black holes, and you probably know more about this, would be in between that.
Between that, okay.
If I remember right, you guys worked out the primordial black holes, so they're, I believe.
Okay. Okay, so you're meaning that thin wall. So in this case, the reheating time scale is longer than PBH evaporation case?
For thin wall, I believe so, yeah.
Okay, okay.
Faster. And I would actually love to chat with you some more about that, because I think that's going to be key to potentially disentangling. So if we see a poltergeisty signal, how do we know whether it's primordial black holes or Q-walls? I really think that that's going to be the key to disentangling these signals, and that's not something that we've looked at in detail yet.
Okay, thank you.
Okay, are there any other questions? Maybe I can ask something while people are thinking. So if you go to your signal, gravitational wave signal, in fact, this may be something related to what you answered. Oh, yeah, here. Yeah. So do you know what is the slope of this peak?
Not off the top of my head, I'm sorry.
Oh, okay. I mean, because that's something that may distinguish. I mean, I have, this may be able to be distinguishable and be measured by these experiments. And you have also this kind of curve and then a slope. So if it is inside the same experiment or even crossing two, it seems, so maybe the slope, it seems like really, is that really vertical or is it not? at
It's not
the
truly vertical, you know, and so here the steep cutoff is because these modes don't get amplified at all during the early Mayer-dominated epoch. They are outside the horizon. So one of the things that we're interested in thinking about is if it goes nonlinear, you know, does this continue straight? Can we argue that? Or does this, you know, can we say anything about how this turns off? This side is sloped down. And as the last question was pointing out, the peak height and the slope should also depend on exactly how quickly is this. So here we made the approximation of instantaneous decay for our benchmarks. We need to work through for future improvement. You know, it's not literally instantaneous, and that's going to affect the slope a little bit and the peak height as well.
Yeah. And may I ask, since we are here, how early or how high in temperature can this peak? Can you move the peak? Can you move it all the way in the frequency, or what is exactly what you?
Yeah. So this is basically determined by the equality and decay temperatures, so you can adjust those as you want. So these are the benchmarks we used here. So the decay temperature is really what sets where the peak is. So we're looking at 100 to 1000 JeV to be in the LISA range. One way you can think about this, and then we kind of fudged it to get the equality temperature where you're just at the limit where you can still ignore the nonlinear regime.
Okay. But could you move it to ET or not?
So as you move it, the peak height also changes. So we have not found very many points in our parameter search yet up there, but our parameter search is not done, so I don't want to make too strong claims. So you definitely could move it up there at higher frequencies. The question is it still observable when we do the peak? Yeah.
Okay, thanks, very interesting. So Yasun has another question. Please go ahead. I don't think we are hearing. I think this happened before. I don't know. Did you hear something? No.
I did not.
No, yeah, but it happened before, so I don't know why this is happening. So maybe he'll come back with a question. Yeah. Okay, so okay, so I mean the time for the questions is over, so maybe we can transition smoothly. Well, thank Lauren again and all the speakers of today for the nice talks. And then we can, slowly move to the discussion session. So let me first then introduce the other panelist. I hope he's here. Let me see. So Ioannis Dalianis, yes, you are here. So if you can. Hi. Okay, hi. And I can see Daniel is back. And we have Subodh and Lauren, and I hope we have the other speakers. Yeah, I've seen one more. And do we have also Song Si? I hope he's around. Okay, so I think, well, for those maybe arriving now, but we had today a very interesting session of talks, starting with Daniel giving us a very nice overview of inflation from a numerical point of view, and this very interesting quote they have written. So then we have some new recent progress and challenges that were introduced about this cosmological collider physics. That was also very interesting to see where they are getting. And now induce gravitational waves from scalar perturbations, which also overlaps between different sessions. And we also had this very interesting talk by Subodh about how much we can learn from spectral distortions. I think that was a very interesting talk as well as all the others. So there seems to be a lot of things to discuss. And so if anyone has a question to any of the speakers or follow-ups, something you have thought about while during the day, questions for the speakers, please, you can unmute yourself, write the questions in the chat box, and we can also read them. So that's also an idea.
Hi, can I ask a question?
Okay, yeah.
Yes.
If you want.
So my question is to Daniel, and thank you for the nice talk. So one of the things I was wondering about is that you, of course, talked about the production of gauge fields and bosonic fields, which for which we know have a Bose-Einstein statistics and leads to enhancement. And usually for the fermion production, we believe it is governed by Pauli blocking. So more or less, it's not very significant for the preheating production. So, so my question is that, are there scenarios where the fermion production during preheating may play an important part? And if so, then what are the scenarios to think about?
So scenarios in preheating where you produce a sizable energy fraction into fermions. This is what you are asking?
Yeah. Yes.
Yeah. I mean, it is really not true that fermions cannot be excited a lot during preheating. They can be excited, maybe not as much as boson. So the main difference is, as you said, Pauli blocking. So for instance, if you have a parametric excitation, if this is of a boson degree of freedom, you can build in amplitude, no? Because precisely because they are bosons, you can accumulate occupation number. However, with fermions, because there is Pauli blocking, you cannot grow in amplitude, but you can push further into momentum. Okay, so in reality, for instance, if you introduce a Yukawa interaction type between some fermion-like field, the standard fermion coupled to the inflaton, I don't mean a standard model fermion, because that wouldn't be possible, that coupling directly. But if you introduce a fermion that is, just coupled a la Yukawa with an inflaton, it's totally possible to do preheating with these fermions, and it depends on the Yukawa interaction. And simply the rule of thumb is that if you compare, say, a coupling between a scalar daughter field to the inflaton and a fermion daughter field to the inflaton for the same coupling strength, you are gonna excite more scalars, obviously, because of the fact that you can pump energy into the amplitude of the spectrum. But if there are, imagine a scenario where you wouldn't have any bosonic degrees of freedom coupled to the inflaton, you could still pump a lot of energy into the fermion, and then these fermions, they could represent the reheating degrees of freedom. These people have worked it out. There are papers of this in the early 2000s. The real problem is that these papers are worked out always in the linear regime, where at most you take into account the back reaction of the fermions into the scalar sector through the expectation value of the bilinear of fermions. But to do the full quantum analysis, I'm not aware that anybody has done it, because I'm not even sure how to do it. But the fact that we don't include fermions is just a practicality, because it's so difficult to deal with them, But if you have a sufficiently large Yukawa strength for a Yukawa type coupling, you would definitely pump a lot of energy into them, and people have worked out this. You can look at papers by Ryōto et al., for instance, 2000, 2001.
I see. So regarding the computations in the lattice, does the strategy be same for the fermions, or would you need to change the strategy?
No, completely different, because the problem is fermions are quantum variables. They don't exist in a classical limit. So if you want to introduce them in the lattice in the same way I do, there is a formalism to do this. This formalism, I'm trying to think of the guy who last implemented, but I cannot think of his name right now, sorry.
Gary Felder, is that?
No. Gary Felder has only implemented lattices with the scalar fields.
I see.
No,
Okay.
no, I'm talking about someone in Nottingham, but right now I cannot think of his name. Sorry. The thing is, you can do it, but it amounts for a lattice of n to the 6 points instead of n to the cube.
I see.
Which means it's very penalizing in terms of memory. So essentially, this group in Nottingham, they put forward in the early 2010s this program in trying to compute the fermionic preheating, and also they attempted to do gravitational waves from the fermion excitation, but they could only reach lattices of 32 points per dimension because of this penalty that you need n to the 6 points, you know,
I see.
which makes unfeasible with current technology unless we think of another strategy. So. Yeah, in my opinion, this is the missing point in preheating studies, you know, that we are incorporating fermions only in an effective manner, but not in the out of equilibrium manner that they would be really stimulated in the same manner as any bosonic degree. Well, not in the same manner with Pauli blocking, but in similar spirit as bosonic quantum degrees of freedom, you know.
And do you expect the gravitational wave spectrum, the shape looks same, or do you expect some change, qualitative changes of the spectrum due to the presence of fermionic Yukawa interaction?
I think for a single fermion daughter field, I would expect a single peak in the spectrum. But of course, the shape itself around the peak is very difficult to quantify. I have computations of that. I have a couple of papers on computing the gravitational waves from fermions.
Okay.
But the resolution we had to do that computation was very low, so I'm not sure how good we capture the real shape, but it's a single peak. However, what I can tell you is if you had several fermions coupled to, say, to an inflaton or to a Higgs-like field through Yukawa type of interactions, you would not introduce a stairway signature as the one I was commenting today for boson. I see. They scale in the opposite direction. So if you want the strongest decoupling, the highest the frequency, but the highest the peak amplitude. So if you had a sequence, a multi-fermionic system of all of them coupled with different strengths to a scalar, like it is the case of the fermions of the standard model, you would only see in gravitational waves the peak of the strongest coupled guys, you know, or at least this is what I was predicting 8 years ago in these rough analytical computations I was doing. Yeah.
I see. And then just a final one curiosity. So when you are building up an occupation number of fermions, let's say, do you also expect some kind of instabilities growing in your system, like sinusoidal instability or tachyonic and instabilities, where you might end up in enhancing your signal, because ultimately it's some fermionic occupation number, right?
Yeah, I mean, there can be exponential growth in the occupation number, but always up to 1, okay? And then once you saturate for a given mode, the occupation number to its maximum height, all the system can do is, in order to create more fermions, is to create them at higher momenta. So what you do is you transfer energy instead of into pumping more energies at the same mode, you start creating fermions with higher momenta, until you have no more energy in the system that is pumping the energy. That's the physical picture. So if you want, you create like a broader spectrum, but always limited in amplitude. Yeah.
I see. Okay.
But that still sources gravitational waves, and actually to some extent,
and then at the end of the day, you can also have like a CP violating couplings, right? The Yukawa can be complex, and then you will end up having chiral gravitational wave, right? So the left
yes, actually, I think there is a paper that they compute that in inflation. What was the context? Yeah, you are right. I think there is, and if you have chiral fermions, you can. I'm not sure about the context of this paper, but they were certainly exciting fermions and then creating chiral gravitational waves. I can dig up these references. I'm not being able to remember right now, and tell you later on if you wish.
So I guess also for in your scenarios when you don't have the fermions but you have axion FF tilde coupling, so that FF tilde coupling can also source chiral gravitational wave, right? Because that is a CCP violating coupling, right?
Yes,
Where
it
you
does.
have
It does. This is the mantra, but also, as I was telling in my talk, the level of a chiral imbalance, so the helicity, the difference between one polarization and the other, is not maximal as everybody has thought in the absence of inhomogeneity. So once you plug in inhomogeneity, you start reducing the level of chiral imbalance. So in terms of gravitational waves, it's not clear yet how this is going to affect the chirality of the gravitational waves. I'm guessing there's going to be some imbalance, no, but it's not clear.
Sorry, but Daniel, yeah, just on this chirality, I mean, suppose this non-linearities did not reduce the chirality, but still don't you need like a very high signal to start with to detect chirality? Like a large tensor to scalar ratios. I remember a paper from 2000.
Yeah. No, of course. I mean, about detecting that signal, whether it's even if it's maximally chiral, that's another thing. Here we are only talking about the prospects from the theoretical point of view of whether the signal is fully chiral or not. Detecting chirality with gravitational wave detectors is very difficult, as you know from this paper, I think of the LISA collaboration and follow-ups that were later. Yes, it's really not easy. You would need very, very large signals. So it's not clear. I doubt very much, even this case from axion inflation, even if it was maximally chiral, not clear to me that could be detected, But for me, this is the beginning, of the field. Now, 5 years ago, 7 years ago, we were barely discussing about these things, no? And now we are a lot of people discussing about these things. So eventually, maybe one can figure out, a way to measure chirality with better sensitivity. And therefore, I think it's very important to determine what is really the difference between one polarization and the other in this so well-routine particle physics scenario, which is axion inflation. So I think it's a relevant question still to quantify to what extent the level of chirality might be reduced due to the inhomogeneities.
Yeah, of course. Yeah.
May I ask something that relates preheating with the talks of that we listened to, the last talks that we listened today. Keisuke, please correct me if I'm wrong, but the poltergeist mechanism works well only if you have a sudden transition from a matter domination era to radiation domination era. And this has to be...
Yes.
So, it has to be faster than, for example, perturbative decay can realize, correct?
Yes. If we consider usual constant decay rate, like a perturbative decay in flattened, poltergeist mechanism doesn't work.
Yeah, so I would like to ask if it's possible to realizing the framework of preheating a very fast transition, sudden transition from the let's say from the reheating era where inflaton dominates to a radiation era, to have a very fast let's say change in the equation of state from zero. Let's suppose assume that you have zero due to inflaton oscillations, inflaton condensate to thermalization. Is it possible to realize it via preheating? I mean, to have a very
I know some instantaneous preheating, but I think the problem is that we need to some extent we need to long matter dominated era. So we need to consider some long-lasting oscillation of the inflaton. At some point, inflaton needs to decay to radiation instantaneously. So I think problem is that we need to introduce some turn-on mechanism with some other field or something like that. Yeah, so we need to do something to realize the sudden reheating. Yeah. So yeah.
I'm commenting on this because the signal that you predict is very large, the gravitational wave signal. So one can already put constraints from the data that we have from LIGO, for example, correct? If we shift the peak to the frequency of LIGO, which are high frequencies that correspond to very early era in the universe.
I guess the amplitude of gravitation waves in our work is smaller than LIGO sensitivity.
Okay, so it's below the sensitivity.
But we restrict ourselves to the perturbative regime. Yeah, so if we take into account the non-perturbative perturbations, the gravitation might be larger than our prediction, and such kind of gravitation rates might be constrained by the LIGO observations. But yeah, at least in the perturbative regime, I think that the current LIGO observation cannot constrain the gravitation waves from the poltergeist mechanism, I guess. Yeah.
Okay.
Lauren, maybe you have a comment?
Yeah, so I was just going to say two things with that. I think, so the height of that peak goes as like the 7th or 8th power of the ratio of the beginning and ending temperatures. So you really, if it's a short period of early matter domination, that peak is going to be pretty suppressed. It drops off pretty quickly. And so that's why you need the, 470 for the ratio of the co-moving at the beginning and the co-moving momentum at the end. You drop that down by a factor of 2, well, 2 to the 8th is, big enough to kill the signal. And then the other problem with that is unless you have some relatively low temperature reheating, you're not going to be in the LIGO band. If you like high temperature reheating, you're going to be at frequencies further away.
I think maybe I'm wrong, but I think that LIGO can detect reheating in the range of 10 to the 9 GeV, but I'm not sure about this. But I think that's what I remember.
Well, so what matters
10 to the 9
is
GeV is LIGO, 10 to the 5 is LISA, something 10 to the 4 is LISA, something like this.
So the peak
roughly
that
speaking
is produced by the poltergeist mechanism is set by the temperature at the end of the early matter dominated epoch.
Yeah, that's what I'm talking about.
Yeah, so when we did our calculations, we were finding that preferred temperatures, 10 to the 5 or so.
Okay.
Can I share my screen? Yeah, I have some comments on that. I think there's a.
I think you should be able to share.
Okay. Yeah. Can you see my screen?
Yep.
Yes.
Yes. So this paper is the first paper about the poltergeist mechanism, and that this paper is focusing on the southern transition limit. So I think this is the most how should I say? This is the largest gravitational wave production in the poltergeist mechanism if we restrict ourselves to the perturbative regime. So this is the almost maximum gravitational waves in the perturbative regime. So we can see that this frequency is smaller than LIGO to this design sensitivity, but still, this can be investigated by the LISA or Einstein telescope or something like that. And if we assume,
sorry, I meant LISA when I said LIGO. I am so sorry about that.
Sorry,
I meant LISA, not LIGO when I said that. I'm so sorry.
Okay, yeah. And actually, so assuming this perspective, I have calculated, I have discussed the, how should I say, we can consider the reheating temperature. So this is a result. So if we assume the poltergeist mechanism, and the vertical axis is the Kmax et al. So Kmax is the small scale cutoff, and et al. Is the conformal time at the reheating. And the 450 is the upper bound of the value. So if we consider larger value of this, the density population becomes larger than unity. So we restrict ourselves to this parameter range, and we can see, we can see the correspondence of reheating temperature. So for example, okay, So in this case, the BBO and the D-cycle case, BBO and the cycle can investigate these heating temperature, 10 to the 4, 10 to the 5th. Yeah, so I
Okay.
think
I see.
this might be helpful to understand that. Yeah.
Yeah. Okay.
Okay.
May I ask something last, if possible, because it's related to your scenarios. I was wondering whether such an early matter domination era, for example, when you assume Q-ball domination or PBH domination, could have any impact to the CMB anisotropies in a similar manner to Kerbhaton mechanism.
Actually, so this evaporation occurs before the BBM. Yeah, we are assuming the PBH evaporation occurs before BBM. So I think
Yeah,
I mean, PBH evaporation
like,
doesn't affect any CMB or something like that.
You know, I was thinking about the Kerbhaton mechanism where you have original the Curvaton, like you have a scalar domination, a scalar field that it's not necessarily dominates the universe, but it has a non-negligible energy density that in the end it shapes the CMB sky.
So you are worrying about isocurvature propagation?
Yes, something like isocurvature. Just I don't know if the PBH domination or the Q balls could have any signature at the CMB sky. Isocurvature, so from the isocurvature point of view, yeah.
I'm not sure. I have no idea, but naively, I think that this physics is very small scales. I think, yeah, this kind of scenario doesn't change the large scale, perturbations. I naively guess, but I'm not sure.
Yeah, I'm asking. Yes. I don't know.
In terms of the curvaton, even though we have a scalar field with a large VEV, it's going to be subdominant, so the inflaton has to have more energy than it kind of by definition, and then it goes into radiation. So its energy is the energy density in the scalar VEV during this post-inflationary period of relaxation is going to be subdominant. So you're going to have your typical inflation, then oscillating matter dominating, then radiation domination, while these QLs are made, and then they're going to sit there until they come to dominate.
Okay. I don't know if are there any questions from the audience?
Just a small point maybe. So you can have inflation scenarios with the runaway potential, right? Where you end inflation, but you do not end up having this inflaton settling down to its minima, creating a matter-dominated universe, right? So there you can have other ways of reheating the universe. One can be the carbotonic reheating of the universe or gravitational reheating the universe. And there probably I mean, it would hard to imagine that just an early matter domination came from an inflaton oscillating under minima, right? So probably in those kind of scenarios, something else would happen. I had one small question for Casey actually. So when you talk about induced say second order gravitational wave, so in principle one can also think about third order gravitational wave, right? So like because there is a mixing in the Mukhanov-Sasaki equations of motion, so at the point of time where you are inducing a large second order gravitational wave, I mean, so is it always okay to say that the third order and the subsequent orders of the tensor perturbations are always subdominant and only the second order would contribute, or there can be scenarios where your third order contribution can also become important?
Sorry, is that question for me? So sorry. I
Yeah,
didn't-
I mean,
Okay,
both
yeah.
for you or Lauren, and if any of you can
Okay,
answer.
yeah. Could you say your
Yeah,
question
so,
again? I'm sorry,
yeah.
I didn't quite get. Yeah, sorry.
Yes, sorry. So my question was that, so when you mention induced gravitational waves and you show the signal from the poltergeist mechanism, you explicitly mean second order tensor perturbation, right? So you're cutting
Yes.
off and truncating your equations of motion till the second order, right? Now, my question is that, is it always okay to assume that the subsequent third order induced tensor perturbations is small enough compared to the second order? Because in principle, everything is getting mixed via the Mukhanov-Sasaki equations of motion, right? So is it always okay to assume that the third order induced tensor perturbation is small and we can neglect it?
So you were saying the mixing of what and what? Mixing? You were saying mixing
sorry, mixing means that your first order scalar perturbations is inducing second order tensor perturbations, right?
Mixing of the first order scalar
Scalar.
perturbation. Scalar,
Yeah, so
and,
that scalar, so that is sourcing your second order tensor perturbations, right?
yes.
Yeah, so
Okay, so
then
you're saying that, okay, mixing of the first order scalar perturbation and the induced tensor perturbation.
yes, so my question is that won't you be also inducing at the third order, like not the second order?
Okay, third order, okay.
Yeah, and is it always okay to assume that that is small n enough?
Smaller than the induced gravitational wave case?
Yes, smaller
Okay,
than
I understand. So you're comparing with the second order gravitational wave power spectrum and mixing of the first order tensor perturbations and the third order tensor perturbation, right?
Yes.
Oh, okay, yeah, that's a good point. I think that contribution is smaller than the second order gravitational waves case because okay, so if we consider the first order and the third order tensor perturbations, the one that is roughly speaking the one tensor per spectrum plus one scalar per spectrum. I mean the scalar per spectrum times tensor per spectrum. And on the other hand, the second order scalar perturbations are scalar per spectrum times scalar per spectrum. And if we consider large scalar per spectrum, that is, so second order tensor perturbation is larger than the mixing of the first and the third order tensor perturbations. But I think that might be interesting. Yeah, but at least in the peak scale, second order tensor perturbation is larger than that mixing of the first.
Right. Because of course the peak arises because there is a change in background equations of motion, right? So in one case you have an exponentially decaying scalar perturbation solution, in another case you have an oscillating scalar solution, right? And that sudden change in your solutions of the scalar perturbations is giving you the resonant peak.
Yeah.
So that will also probably be the true for third order as well. Now just one needs to see whether that is small enough. Like probably it will be small enough.
Yeah, probably. Yeah.
But the property remains same, right? That the scalar perturbations obeying the particular solution. In one case you have exponentially decaying scalar perturbation, another case you have an oscillating solution, right? So that property induces your second order gravitational wave, right?
Yes.
And that property will still be true if one considers third order gravitational wave. Now, whether it's
consider what?
So like if you take the third order, right? Like instead of stopping at the second order, if you take the third order.
Higher order. Okay, higher order.
Just a higher order.
Okay, higher order. Okay. Yeah, I think that could be interesting topic. Yeah. Yeah, I'm not sure what happens in the higher order, case. But naively, for example, first on the third order correlation with the tensor perturbation is smaller than primordial one. Naively, because tensor power spectrum times scalar power spectrum, and that means that if we consider smaller, if we consider scalar power spectrum which is smaller than unity, that is that product is smaller than the first order primordial power spectrum. Yeah, I never think like that. But if we consider sudden or some such kind of transitions, I don't know what happens in that case. Yeah, that could be interesting. Yeah.
Right. So in order for your poltergeist signal to make work, one has to find out the the parameter space where we can make sure that the other higher order contributions are small enough, right? So that we can get that exact section, or else maybe some other signals are modifying the exact shape of the spectrum.
High order contribution might be important. I've never calculated that. So but that could be interesting.
It's interesting. So I don't know if there are any other comments from the audience, from anyone. To all the speakers, I think we missed one speaker. So okay, unfortunately that's. But I don't know if there are any other things anyone wants to comment on. On all the.
Can I ask a question to Lauren? Okay. I'm so interested in the mass spectrum of Q-ball. So you are saying that Q-ball mass distributions tends to be very sharp. So how sharp it is? Can we how should I say get some quantitative estimation with the how sharp the mass spectrum?
So this comes from simulations, and I'd really love to see some more detailed simulations. So the gauge mediated SUSY breaking simulations show very, very sharp, because there's kind of a cannibalization thing going on, where in each Hubble volume, one QL ends up getting all the charge. It just shrinks into a single QL. And so in that case, those simulations show a really, really sharp peak. I don't know the width off the top of my head, but those, when you look at those simulation papers, which I can send you, they're really sharp. It's less clear for the gravity mediated case, because there's not really this cannibalization where it's one cue ball grabbing all the charge it can get. And so there they tend to get roughly 1,000 or so QLs, and there is a broader peak with it in the mass distribution. But one of the uncertainties there is that there really hasn't been a whole lot of simulations of gravity mediated that have a highly elliptical behavior of the VEV, because that is computationally hard, so I don't run these simulations, but they tend to have a rounder VEV. And so that leads to a great deal of uncertainty there. So there are some plots that show the width. I don't have the numbers off the top of my head, when you have kind of a rounder VEV, and it seems to still be relatively peaked when you go to an elliptical one, but without some sort of simulation, we really can't say for sure.
So if I remember correctly, so you were saying that decay rate depends on the thick or thin wall approximation. I don't remember, but so you are saying that gauge mediation case predict a very sharp peak, and which one is the which one leads to the rapid subheating thick wall?
So both thin wall and thick wall have nearly instantaneous decays at different rates. So both of them have the decay rate over charge goes as a negative power of the charge. And the thick wall, that's the one that we are currently working out.
Okay,
That
thick
one
wall, okay.
actually has a stronger negative power. And so that would be the case that is the most promising, because that's where you have the cannibalization. And so you would have a very, very sharply peaked
Okay.
spectrum. And that's
Okay,
also where you have the fastest rate.
Okay,
For
so,
the paper that we
yeah.
published. So those calculations we're wrapping up and hope to get the paper out maybe by the end of the
Oh.
year, which would be
That
nice.
sounds
For the PRL, for the first one, we did everything in the thin wall regime. And so those apply.
I see.
uh,
Okay, so
more
at
straightforwardly.
this stage, the most promising case is the gauge mediation plus thick wall case.
Right, and
That's
so
the-
gauge
okay.
mediation does, the QLs that you get in gauge mediated are thick wall, you know?
Okay.
So it depends on the potential, basically, the shape of the potential, whether you get thin wall or thick wall. And so
Okay.
that's not something you
Sounds
can
interesting.
predict directly from the potential.
May I ask something last, Subodh Patil?
Yeah.
I'm not expert on this, but maybe my question is naive. So people who predict gravitational wave signals, a gravitational wave background coming from the early universe, the main obstacle to test this model is the astrophysical foreground. So have astrophysicists predict huge foregrounds, a huge gravitational wave background, and it's very hard to figure out if there is a detection of gravitational wave background. It will be very difficult to figure out if this comes from a stellar astrophysical source or it has a cosmic origin. So, but there is a very significant difference between the gravitational waves that have astrophysical origin and those that have a cosmic origin. And this difference is that the gravitational waves that are produced in the early universe, they propagate the universe for billions of years. So they might affect. The question is if the gravitational waves that are produced in the first second of the cosmic evolution could affect the CMB at smaller scales. It's well known that the B-mode polarization can give us information about the gravitational waves coming from inflation. So if a signal that's produced at higher frequencies could affect the CMB. I'm asking this because, for example, the Y and U distortion, as far as I understand, can give us constraints about the power spectrum at smaller scales compared to the CMB scale. So is it possible to give us also constraints the CMB at smaller scales than CMB about the amplitude of the gravitational waves produced in the early universe? In principle,
Yeah, so the thing is, one of the many different sources that
We hear you very low.
Sorry?
I was not hearing you almost.
Oh, can you hear me now?
Yes,
Now,
we
yes.
were not able to
Yeah.
hear you.
Yeah, I was saying that the thing is about gravitational waves from the early universe is there's many different sources, and we have to really think about the different frequencies at which they're produced and which they're produced. So and also their spectral shapes. Okay, so the thing that we think comes from inflation or vacuum fluctuations, vacuum tensor fluctuations, and they're very roughly scale invariant with a logarithmic dependence, which is natural to their nature as a vacuum fluctuation. Any physical process that produces non-vacuum fluctuation, things on top of it, which is
Sorry, we are not able to hear you properly. Can you maybe? Yeah.
Okay, so is this better?
This is better.
Yeah, sorry. I was saying that so what we can see in the CMB, or what we'd like to see in the CMB are tensor modes from from inflation, if they are indeed there, or something else. Those are vacuum fluctuations, and so the nature of vacuum fluctuations that they're very weakly logarithmic running. But anything that's a physical process typically has a very distinct spectral shape. Okay, and it's going to have a peak. Let's take first order phase transitions, for example. They don't exist in the standard model as we understand them. So at least the way we understand the standard model as it is, you have to add some new ingredients. If they're dark sector phase transitions and they start coming in at frequencies that spectral distortions are sensitive to, or I mean, this discussion could be broader than this. There are no astrophysical foregrounds that could produce gravitational waves at those scales. There's literally nothing in the sky that can oscillate at those frequencies. It's really, really, PTAs are already fairly large scale objects. If your question is how do you disentangle different things, it really comes down to the spectral shape, but you also have to have a solid prior for what that shape had to be. So, for instance, what if there was a large background of, supermassive black hole mergers, for instance, right? We have, a fairly good idea of how galaxies formed and how, the structure of the evolution of the universe evolved. So that shape is not going to be completely, out of range. The kind of probes of the kind of frequencies that spectral distortion and the CMB probe for gravitational waves I just can't imagine any astrophysical foreground that can get anywhere near them. I think one of the more interesting things to me probably is going to be discussed tomorrow, is actually what happens at very, very high frequencies, because there actually it's impossible to get astrophysical frequency black holes. We're talking like gigahertz or megahertz frequencies. There's tabletop experiments that are actually trying to get to measure these kinds of frequencies, and this really would be so particle physics can produce sources like this, of course, right? So there's a standard model background, in fact, from the QCD transition. It doesn't have to be it can be a crossover and you still get gravitational waves. It doesn't have to be for first order phase transitions, of course, give you many sources of gravitational waves, just either from bubble collisions, from turbulence, from sound waves in the bulk plasma. So these very high frequency gravitational waves are almost exclusively going to be a part of the physics origin. So yeah, I don't think there's one clean answer to your question, really, but I think it really depends on what frequencies are you looking at. Astrophysical gravitational waves, I cannot imagine anything clipping deep into the spectral distortion window. Of course, towards like the end where there's a little bit of overlap with pulsar timing arrays, but the sensitivity drops out pretty fast. And I should also stress the gravitational wave sensitivity is very bad for spectral distortion. I mean, I think the most you can hope to get is about omega 8 squared of about 10 to the minus 6, 10 to the minus 7, right? Which is not very good. But nevertheless, there's nothing else. You need to build a detector that big, right? Of some kind, and PTAs are the biggest detector we have. So it's sort of like an indirect probe. Yeah, I'm not sure I answered your question in any convincing manner, but I would say, on a case-by-case basis, you have to understand what you're looking at, what source you think you have. And in general, actually, it's a bit of a I'm not sure how the right way to phrase this is. There's sort of like an inflection point of how you win and how you lose, in the sense that signatures, backgrounds that have a strong spectral shape, right, like a very distinct spectral shape, a big knee and like a peak frequency. In some sense, you think, okay, then maybe they're easier to detect because you know what spectral signature you're looking for. But actually, what happens for very flat, broad signals, like really stochastic background with a very sort of power law dependence, is you have the advantage of also integrating over frequency bins and not just time. So the sensitivity curves actually go up quite a lot for those relative to a raw sensitivity curve of just having a delta function type signal at that scale. Yeah, I don't know if that answers your question, but one really has to think about it on a case-by-case basis.
Yeah, thanks for the answer. Actually, it's
sorry, just a small point. So when you mention high frequency gravitational wave, can't you we imagine very light primordial black holes? they are merging, and that can source very high frequency gravitational wave.
I think you need things that would have already Hawking evaporated away to get a signature at those frequencies, right? Very light primordial black holes evaporate fast.
Yeah, but still there might be a slight window.
Are you referring to mergers of primordial black holes?
Yeah, mergers. Yeah.
Well, okay. First think about it, right? So they have to find each other and merge. You have to calculate merger rate. So that's already crazy. But also megahertz, right? I mean, you really need these two things to oscillate. You know, it's a physical excitation, right? Anything astrophysical has to really. I don't think so. I don't think there's any primordial black hole signal from mergers that will get anywhere near megahertz. No way. I mean, this is my back of the envelope reasoning. I could be mistaken, but I'm just thinking about you're literally asking for something. Remember, the frequency of primordial gravitational wave radiation from mergers is twice the Schwarzschild radius just before the merger, right? So, what is the inverse Compton wavelength of about 100 megahertz? Actually, it's not so bad.
So I'm thinking about very light
centimeters, right?
Yeah,
I mean, okay. First of all, you need enough of them, and you need to have them merge.
Yeah.
You know, that's kind of a big order. I mean, super light primordial black holes. You know, I don't know. So here's the other thing that is somewhat frustrating from the perspective of people who may entertain primordial black holes as an interesting thing to think about is I don't think anybody has really, precisely because there's so many moving parts, these computations are hard, have done an actual simulation, a convincing enough simulation to be able to forecast merger rates in a very convincing way, right? It's a big unknown. Probably because it's a very difficult problem and it's going to be a very thankless task. So I think a lot of people, I know people have sat down and said, okay, I'm going to do this, and then they give up because they see the mountains they have to climb.
True, that's true.
It's a really crazy computation. And someone should do it, but one only has a finite amount of time.
Yeah.
Okay, so I think we are getting to the end of the session. I think it has been very long, so I think we should just thank all the remaining speakers that are here today. Thanks for the talks and the discussion and the remaining participants as well. So thanks everyone, and hopefully tomorrow we'll have.
I'd also like to thank you, Yvonne. I think I was studying but you're a role model of chairing a session, keeping everybody on time. It was something that we can all learn from.
I was going to say the same. Thank you.
You were there as a chair last year, right? You are.
Yeah, I think so. I don't think I was as good as Yvonne. I let people slip. So.
Yeah, indeed. So okay, but we are doing is 2 to 7, so I think we are just ending perfectly on time. So unless there is like a last thing someone wants to say, I think we can close the session here and then come back tomorrow for the last day of the workshop. So thanks everyone.
Thank you for the one session.
Thank you. See you tomorrow.
Bye.
See ya. Bye.
Thank you very much.